Hello, my name's Amanda, and today I'm going to be going over the proof of the derivative of e to the x. Now, this is the only function whose derivative is itself. I'm going to show you why right now. But before we start, there is a really important definition that you should know, and it's a way of expressing e. So e is the limit as n approaches infinity of 1 plus 1 over n to the power of n. Another way of expressing this is the limit as m tends to 0 of 1 plus m to the power of 1 over m. Another important thing you should know before we start this proof is how we differentiate from first principles. Now, I'm going to give you the formula right now, but please do watch my previous video on differentiating from first principles if you don't know how to do that already. So let's say we have a function f of x. The derivative from first principles will be the limit as h tends to 0 of f of x plus h minus f of x over h. So, now that we've got those out of the way, let's start proving this result. Let's say our function f of x is e to the x. So, as we take the derivative of the function, so d of dx of e to the x, when we differentiate from first principles, we're going to get the limit as h tends to 0 of e to the x plus h minus e to the x over h. Now, hopefully you can spot that we can factorise the numerator here. So I'm going to carry on the limit as h tends to 0 and take out e to the x to get e to the h minus 1 in the bracket. Now at this point, I really want our limit to look like the limit I introduced to you at the start. Why don't we first take e to the x out of the limit? Why can I do this, you may ask? We're taking the limit as h tends to 0, not as x tends to 0, so the e to the x will be unaffected. So I can just whip this out of the limit. Now, if we take the limit right now as h tends to 0, we're going to get something like e to the 0 minus 1 over 0. E to the 0 minus 1, that's going to be 1 minus 1, which is 0. And our denominator will be approaching 0. So then we get something like 0 over 0, which is just going to cause a lot of problems. So we need to keep manipulating this limit until we get something very nice. So, why don't we get a substitution here? How about letting p equal the numerator? So that's going to be e to the h minus 1. So I'm going to move the 1 to the left-hand side to get 1 plus p equals e to the h. Now I'm going to take ln of both sides to get ln of 1 plus p, and with the right hand side, so I'm taking ln of e to the h, bring the h down, so you're going to get h of that, and we know that ln x and e to the x, they're inverses of each other, so we're going to get h times by 1 here, so it's just h. So, now that we have h, and we have p, I'm going to substitute this back in now to what we had originally before. So now I'm going to rewrite this, so we're going to get d by dx of e to the x is e to the x limit. I'm now going to switch this up to p tends to 0. I'll explain why in just a second. And then remember, we're replacing our numerator with p, and we now know what h is, ln 1 plus p. So, the reason why I'm replacing h with p here, when we're looking at the limit, is that we already know that p is e to the h minus 1. So, as h tends to 0, p is going to tend to, well, think about it, e to the very, very small positive number, it's going to be 1, and then we're subtracting 1, so it's going to be 0. So p will also tend to 0 as h tends to 0. Hopefully that makes sense. And now, why don't we divide both the numerator and the denominator by p? So I'm going to get e to the x, the limit, as p tends to 0. So p divided by p, we're going to get 1, and then we're going to get 1 over p ln 1 plus p. Now hopefully you should have an idea of what to do next. If you don't, please pause this video and look back to deriving the laws of logarithms video. It's one of my early videos. So I'm going to rewrite this now as e to the x limit as p tends to 0 of 1 over, hopefully you spotted the trick, we're going to bring the power up this time. So we're going to get ln of 1 plus p, and that's going to be to the power of 1 over p. But be careful here with the brackets. I'm just going to bracket this. 1 over p, and then close the square bracket. I'm looking here at the lim p tends to 0. Is there a way of linking this limit to the limit I introduced to you at the very start? This one here, the e one. If we look at the second alternative here, it's looking rather similar. But I think we can do a bit more manipulation to get it exactly like this. I'm going to bring the limit into the ln. I'll show you what I mean in a second. So I'm going to get the ln, and then here, bring the limit in. So limit as p tends to 0 of 1 plus p to the power of 1 over p. I'm just going to have to extend this line here. Okay, now hopefully this should be screaming a letter to you. Is it E? I hope so. And if you're thinking that, You are definitely correct. So you're going to get ln of e. Now, do you remember what we said at the start? ln and e are inverses of each other. So it's just going to equal 1. So we get e to the x times by 1 over 1, which just leaves us with e to the x. So, that's the proof for you. I really hope you enjoyed it. We did need a few things in order to carry out this proof. The two things in blue here. But hopefully that makes sense. And I think it's a really crucial proof in differentiation. So, very well done if you managed to get to the end of this video. Thank you for watching and have a lovely day.